motivations to work on this model. Basically, what we want to do is try to exploit the flexibility of the cloud, right? And exploit it to keep, to try to maintain two conflicting objectives, right? To keep this trade-off between the costs and the quality of service that we can have. And we will focus basically on the quality of service. What is it that we want to do for this? We want to build a good model of the application, so we want to consider the application architecture, we want to consider the workload that the application will face, and we want to consider also the characteristics of the deployment. So, and this is actually something that will be changing, so the model should be able to, based on this information, build a model that can be solved in an efficient way, and that can let you explore at design time, right? Do this part of the QoS analysis at design time, but also that you can keep the models alive at runtime, such that you can improve or modify the decisions that you have made before based on a change in the application architecture, in the workload, or maybe in the characteristics of the deployment. Maybe because you switch from one cloud to another cloud. So what we are based on to do this description are Palladium component models. So the good thing of Palladium component models is that this software engineering will let us specify by means of a different set of models. It let us specify exactly these three characteristics that we want to model, to capture, to actually have a good description of the application, to have a good model for QoS analysis. So what's our contribution? Basically, the first step that we do is that we start from these Palladium component models and we do an automated transformation from that one to a performance model. So there's no need to do anything additional to just specifying the models that are already in the Palladium component model. And then this model has a number of characteristics. I will talk about them later. But the last one is the one I want to stress here now. It's a fluid model. So in some sense, it is an approximate model, but at the same time, it lets us have lots of information that, because of a number of issues that are known from traditional models, can be really computed for large systems, like using markov chain analysis, for instance. So what do we get with that? So we get an effective method to assess service level agreements in terms of percentiles, not just averages, but also percentiles, SLAs. We are still able to compute long-run measures, performance measures, but also transients. So given at some point, given that the system is in some state, we can compute what's the expected performance at that point in an efficient manner. So what do we do it? And this is like, I will focus on how we assess this percentile SLA. So there are alternatives, right? You can run a simulation. So simulation is very good because you can have a very accurate model of the application, right? You can capture many different details, very minor details of the application. You can capture them. You can actually compute, like estimate the response time distribution, for instance, so you can actually assess if a percentile SLAs of 95% of requests of this type should be completed in at most this time. You can assess that sort of thing. And it's already available if you're thinking in terms of Palladium component models. The Palladium bench tool already includes this Simicom, which is a simulation tool that lets you do exactly that. What's the problem? That it's very time consuming, right? You need to run each simulation. It takes a lot of time, especially when you have events that happen that are very unlikely to happen, right? Like unavailability issues, for instance. So this is very unlikely, so you will have to wait a lot of time until one of these events appears in the system. And this, of course, then limits what kind of scenarios, how many scenarios are you able to actually look at. There's another option, layer 3 models. it's a very good option in the sense that it also tracks, it gives a very accurate description of the application. Maybe it's not as accurate as the simulation, but it is able to describe many of the details that you would like to describe, like synchronous calls, blocking the first in the application deployment, and it is scalable. So it is based on an analytic model, so you can actually run many instances, consider different scenarios, and it's very easy to do. And it's also ready in the Palladium Bench tool. So there's a transformation that takes you from the PCM instance to a layer queuing network, and then you can use something like the LQN solver to find the solution to that system. But the issue there is that this solution is in terms of mean, average measures. So you get like what's the average response time, right? But the average response time can be very far from what's actually the 95% or something. So it's not really, you can do tricks that are like, you can add some constants or that sort of thing, but that's not really, you are not really sure of if what you're doing is actually correct for all cases that you're considering. I want to highlight this PCM to LQN transformation because we will make use of that, or we make use of it. Alright, so what's the performance model? So it's a queuing model, it's a closed queuing network model. It allows like many types of requests, and it has a feature that adds a lot of flexibility, which is class switching. So basically, if you have a request that comes to the same server, and each time it visits the server, it has a completely different type of completely different processing time, right? Because it's the same user that's doing a different number of tasks, and each of these tasks is different in a very meaningful sense. You can actually do that with the class switching. And the last characteristic is that it is a fluid model. So a fluid model is basically a set of ordinary differential equations. You can derive it if you start from a Markov chain definition. You start from your Markov chain, and you can actually, it's not that you, I mean, this model appears as a limit of the Markov chain. I won't go into the details of that, but what's the good thing of this kind of model? Basically, you avoid space explosion. So one of the big problems of Markov chains, if you want to solve the Markov chain, the beauty is that you can go too far with the Markov chain because it will easily grow out of hand. Right? There's the curse of dimensionality. You will have like millions and billions of states, and you won't be able to solve the linear system that you need to do to solve to find performance measures. So it is an approximate method, but it provides you with a time-dependent solution. So you not only get like one point, which is the long run time average, the long run average, but it is a history of the system, of how the system behaves. And if you have a rather large system with a large population of users, you can actually prove that this system is exact when there's a large system. So you have a number of stations, you have a number of classes, you have a number of users, of worker threads or requests, depends on the abstraction that you want to make. You have this routing probability matrix. It's actually also a switching matrix. You visit the stations, right? And each time you visit a new station, you have the probability of changing the type of request that you're serving. Okay, and we are considering a general number of servers, so we don't have like limitations on the number of servers that are sometimes necessary. We describe the state, knowing how many requests of each type are in each station. Very simple, right? That's all you need to do. And then we have some transition rates. And here I want to just point out something, right? These transition rates are a bit different from what we find. It's like a combination of things. So if you look at the first term, basically what it says is, if there are less requests, the number of requests in a certain station, a certain server, is less than the number of available servers, say CPUs. Yeah. What we are assuming is that each of these requests is being served by a different CPU. Once you get the system loaded and all the CPUs are working, then you say, okay, from this point on, this will work as a processor sharing processor, and you will have like, if there are 5 CPUs, you will have 5 times the capacity of the single CPU. This is not like the usual equation that you will find. It's like a combination of first come, first serve in the first case and processor sharing in the second case. But it has some nice analytical properties that help out. And actually, it's actually interesting because you don't need to keep track of individual CPUs, for instance. You can just look at the whole system and you get some sense of how it will behave. So, you put these rates, right? I'm here defining the rates, and then you say, okay, this is the ordinary differential equation that I'm going to solve. It's basically you put in the rate, the jumps, and you solve. This is how you solve this equation. You hope, and it's usually the case, but we still have to prove that there is a fixed point, right? So you let the system evolve until basically the derivative disappears, so the system remains at some point. Once you get there, you can actually extend this ODE system, and we go into those details, to compute the response time distribution. So you go to this fixed point, and from that point you can say, okay, I do some additional trick, and I can compute the response time distribution. So even though the system is like an expected, it uses an expected value type of approximation, once you, it lets you compute distributions, not only expected values. And you solve this extended ODE. So what's the point of the response time distribution? Basically, it lets you know for every time t what's the probability that the response time will be at most t. And this is exactly what you need if you want to assess percentile SLAs, right? So basically, if you have a percentile SLA of that kind, like y% of class K users or requests need to be completed in less than 10 milliseconds. This is equivalent to know that the response time distribution evaluated at point t is at least equal to y. So here's an example from this milliostore application that has been used before with the parallel component models. And this is the SLA. So on the x-axis you have the time, and on the y-axis you have the probability. So you say, all right, my SLA will be this. 95% of my requests need to be done in 1 second, right? So you would like to find, to be sure that if you have a distribution, it should lie above this point, this crossing point. So this is a simple example. I take one disk. This is done for the database disk for this application. So I put one disk and I compute the response time distribution, and I obtain this dotted dash line. So what is it that I get? If I look at the 95%, right, point there, so what I see is that I can only ensure that 95% of the requests will be served in less than, say, 4.5 seconds. So this is not what I want, right? And actually, if I would like to look at how many of them are completed in 1 second or less, it is less than half. So you say, okay, this is not enough. This is not what I need. Even though you might go look into the average response time, and the average response time might be fine. I mean, it might not look too bad. But if you look at the 95%, it can be very far from the average. So I add another disk, and look, this is example that this should happen, because you do one step and you're there. And basically what you see is that in this case, 95% of the requests are finished like in half a second at most, and actually in 1 second.